A set in math is a group of things, in this case numbers. The things inside of a set are called elements. An infinite set is just a set with an infinite amount of elements. For example, the set of all natural numbers, 0, 1, 2, 3, 4, 5, 6, you can include and not include 0, it doesn't matter. And if you keep on counting and add all these numbers as a set, this set has an infinite amount of numbers or elements, and therefore it's an infinite set. Also, the set of 0, 2, 4, 6, 8, until infinity, which is the even numbers, is also an infinite set, because it has an infinite amount of elements. The real question is, which set is bigger? Is the set of natural numbers bigger, or the set of even numbers bigger? And are there even bigger sets, or smaller ones? Well, a famous mathematician named Cantor answered all of these questions. It all comes down to what's called one-to-one correspondence. I'll explain. If you have two finite, non-infinite sets, and you want to find which one is bigger, well, you can use what's called one-to-one correspondence, where you correspond or connect each and every element of one set to each and every element of another set, and vice versa. So I can connect 1 to 1, 2 to 2, 3 to 3, and 4 has nothing to connect to, therefore set B is bigger. And it doesn't matter how I connect them with one-to-one correspondence. If I connect 1 to 2, 2 to 1, 3 to 4, and then I have 3 left, and I know set B is still bigger. And this is called one-to-one correspondence. What Cantors said is that you can use one-to-one correspondence also for infinite sets. So now to answer the question, which set is bigger, the set of natural numbers or the set of even numbers? Well, let's see. Let's try to just find a function for doing one-to-one correspondence between them and see if it works. So, between the set of natural numbers and even numbers, I can just do each one of the numbers times 2. So 0 to 0, 1 times 2 is 2, so it's 2. 2 to 4, 3 to 6, 4 to 8, 5 to 10, and infinitely. So for each and every element in the natural number set, I connect to an element in the even number set. So now let's try to do the opposite. So I can try to do from the even number set to the natural number set by dividing by 2. So from 0 to 0, from 2 to 1, from 4 to 2, from 3 to 6, from 8 to 4, and it continues on infinitely. And therefore, because there's a one-to-one correspondence, meaning in all the elements in the first set, I can connect to a different element in the second set, and in each and every one of the elements in the second set, I can connect to a different element in the first set. And therefore, even though one has, let's say, 3, or all the odd numbers that the second set doesn't have, because of one-to-one correspondence, if we define the measure of what set is bigger in infinite sets as being, if there's one-to-one correspondence and they're equal, which is the only thing we found that actually works. I mean, there's a couple of other things, but this is the common way of doing it. Then we find that the set of natural numbers has the same amount of elements, so it has the same size as the set of even numbers, which is a bit counterintuitive. But if you think about it, why should one infinity be bigger than another infinity? And it works. Now, what Cantor tried to do, and he managed, is try to find an infinity bigger than this infinity of all the natural numbers. The infinity of all the natural numbers is called Aleph Null. And this is what's written here. Aleph, the Hebrew letter Aleph, with a 0 next to it. And this is its name, the infinite set of all the natural numbers, and all of the infinite sets that can correspond with one-to-one correspondence to the natural numbers. So, what we want to find is Aleph 1, which is something, an infinite set, that has extra elements that we can prove that they can't be corresponded to Aleph Null, to Aleph 0. And then, if they can't be corresponded to Aleph 0, then they have extra elements, and therefore, they're bigger than Aleph 0. So, what Cantor did is he used what's called a power set. Let me explain. A power set is written as a big P with two braces and the set you're trying to get the power set of in the middle. So if I have a set, and I'm going to set that set as having 1 and 2 inside of it, so this set J, contains the number 1 and the number 2, and I want to find the power set of it. Well, the power set of 1, 2 will be a gigantic set, which contains a set without anything, an empty set, a set with only 1 inside, a set with only 2 inside, a set with 1 and 2 inside. So, what is happening here? What does a power set actually do? Well, the power set contains all the possible combinations of either adding a number to the set or not. So, this one is not adding any number. This one is only adding the first. This set is only adding the second. And this set is adding both of them. So, it's all the possible combinations of either adding a number or not adding a number in the set. So, this can be represented like this. Here, where 1 corresponds to y, 2 corresponds to n, and y means yes, n means no. So, if it's written y, I know I add the number to the set. If it's n, I don't add the number to the set. And now, this yn means this set, the set with only 2, because only 2, the set with only 1, because only 1 has a y next to it. And if it's yy, then it's the set with also 1 and also 2. If it's ny, then it's the set with only 2. And if it's a set with nn, then it's the set with nothing, the empty set. And it's all the combinations. Essentially, a power set is all the combinations of either n or y for each and every element. So, because it's either n or y, which is 2, so all the possible combinations will be going through going through all the elements in the set J, and then each time, because there's 2 possibilities, multiplying by 2. So it's 2 possibilities, times 2, which is 4. And that's what we got before. We got before 4 possibilities, 4 elements in the power set of J. 1, 2, 3, 4. And it can also be written as 2 to the power of the number of elements in the set J. So, if J has 2 elements, so it's 2 to the power of 2, which is 4. 1, 2, 3, 4. That's it. So, what the mathematician Cantor did is he found that the power set of Aleph Null, which is all the possibilities of either adding a number in Aleph Null or not, is bigger than Aleph Null. And he called it Aleph 1. And why is it bigger? Because each and every element in Aleph Null can be corresponded to an element in the power set of Aleph Null. And there are elements in the power set of Aleph Null that can't be corresponded to Aleph Null. It's a bit counterintuitive, but here is his proof. Aleph Null is all the rational, all the natural numbers. So 0, 1, 2, 3, 4, 5, 6, 7, until infinity. Doesn't matter if you count 0, don't count 0. Now, if I want to get the power set of this, so what that essentially means is if I have an n or y next to each one of these, then it's all the possibilities of either having n or y. And n or y can also be represented as 0s or 1s. So I wrote 0s or 1 here. So what I'm doing here essentially is listing all the elements of the power set of Aleph Null in opposite binary. So I take binary numbers and then turn them around so it will fit to my structure. So this is 0 in binary, this is 1 in binary, this is 2 if I turn it around, and this is 3. So I can just keep on going like this. And then if 1 represents adding the number and 0 represents not adding the number, then if I keep on going, then I should have all the possibilities of either adding numbers or not adding numbers, all presented in binary numbers. And because it's binary numbers, I can list them like I did here, and then I can correspond these to Aleph Null. So it looks like I solved it, right? Right over here, 0, 1, 2, 3, and continuing are all the possibilities of power set of Aleph Null. And 0, 1, 2, 3, 4, 5, 6, and continuing is all the elements in Aleph Null. So I can just correspond them, right? Well, what Cantor did is called the diagonal argument. And the diagonal argument shows that this is actually wrong. There are more elements, there are more sets, infinite sets, that I can't include inside of here. They're by definition different than all this list of sets. And there are an infinite amount of them. So the diagonal argument goes like this. If only one digit, meaning one number either being added or not added, is different between two sets, then the sets are different. So if I construct a new set down here that's different than all the sets before by only one digit, only one number, then this new set will by definition be different than all the rest of the sets. So I can come from the top over here, and in my new set, I'll do the opposite. So instead of writing 0, I'll write 1. And then I go to the second digit, and instead of writing 0, I'll write 1. And then the third. And each time, I write the opposite of what's written here. And then altogether, if I construct this infinite set as being, by definition, the opposite of this whole diagonal, then this new set will, by definition, be different than all of these sets. And it makes sense, because all these sets are eventually, even if you get, it doesn't matter how far you go, eventually they'll always have 0, 0, 0 in the end, until infinity. And this new set I constructed upon these sets changes forever. It can go 1, 1, 1, and then eventually it will start changing and changing and changing, because it gets into where there's starting to be 1s. And when it sees a 1, it does the opposite. And because in each and every place, it has, for each and every set of these, a place where it has a different digit than these sets, then it must be different than all the sets before. And it's not, I can't only start from here. I can start from here, but I can also start from here, and from here, and from almost any place, and going diagonal. And then I have an infinite amount of sets that aren't in this list. So what do? I mean, it doesn't matter how I set, in what order I set, or how I set these sets of the power set of Aleph Null. I'll always be able to do the diagonal argument, right? Well, let me try to go over that. So there's a supposed hack. This hack is called computer code. This computer code doesn't actually do anything, but I can set all the computer codes in the world, which means all the functions, all the computable functions in the world, in order where a countable order. So because they use alphabet, I can just list them in alphabetical order, all the possible computer codes in the world. And then if I can list them in alphabetical order, that means that it doesn't matter what trick I do here, or how I go diagonally or whatever, I'll always have a computer code that does exactly that trick. Whatever function you do to try to get a new set, I'll have a computer code in my countably infinite set, which means a set that can be corresponded to Aleph Null, that does exactly that trick. And then you can't play any tricks on me, right? And I can take each and every computer code that eventually, even if it takes an infinite amount of time, spits out or returns all of the elements in a set, And each one of those computer codes that returns a set in order of magnitude in the size Aleph Null, I can correspond to elements inside of Aleph Null, which are just the power of prime numbers. Because if I do 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, it doesn't matter what power of 2, it will be different than any power of 3 that's 1 or larger. It will be different than any power of 5, and than any power of 7, and any power of 11. Because of the fundamental rule of arithmetic, it says that each and every whole number has only one set of prime factors. So it seems like I found a way to do a one-to-one correspondence between Aleph Null and all the possible functions in the world, all the possible finite functions in the world, and therefore, even if you do the diagonal argument, then that will be included. So it looks like I hacked it, right? Well, not so fast. Because there's no reason why there shouldn't be functions. There shouldn't be sets inside of the power set of Aleph Null that don't have a function behind them. It could be random numbers, and it could be just numbers like 3, 4, 5, 2, 3, 4, 1, 6, and continue on, with no functions behind them. So my computer code thing worked for all the functions that could be generated using a computable function. But this breaks everything, because if you have a function, if you have a set that can't be computable using a function, for instance, a random number generated set, then you can't, this new set can't correspond to the elements of Aleph Null, because I can't list it. And that's why the power set of Aleph Null, which Cantor calls Aleph 1, is in fact larger than Aleph Null, because I can correspond every element of Aleph Null to Aleph 1, but there's those weird sets in Aleph 1 that have no order and no function that I can't find any way to list, and therefore I can't correspond them to Aleph Null. So that's how I found that's how Cantor found a bigger infinity than infinity. And this trick of the power set of Aleph Null also works for Aleph 1. So if I do the power set of Aleph 1, it will be Aleph 2, because I can't, and the trick still works, and I can do more and more and more. And that's why I said that there is Aleph Null, Aleph 1, Aleph 2, Aleph 3, and each one is a bigger infinity than the other. Thank you for watching, and please argue and ask questions in the comments.